or something like that. Integrate all those messages. Very cool.
So last week we discussed about the driving circuitry for the SR motors. So you can see that each of the winding we're going to connect by two IGBT or power MOSFET. So you can see that we tend to, the winding will be put between the two transistors, so each of the phases will be highly independent from others, because we know that we usually will turn on one by one. So that's to say, when we want to operate on the A phases, the S1, S2 will turn on, all the other phases will be disconnected. So in this way, we make it highly independent. So as we know that for SR motor, the key thing will be able to have the fault tolerance. In case any one of the winding, say the B phase broken, short circuit or whatever, you can also able to this phase will not affecting all the other phases. So you can just turn off the two transistors. So that's why this arrangement can be really reliable, much better than all the other motor drive systems. Yes?
In your control, how would your control know that your B winding is not working?
Certainly, we can support we do have a thermal sensor for each of the winding. For instance, if any short circuit here, the current will be really large, then we're able to detect that. All the IGBT or power MOSFET internally they have a current sensing. So that's a high standard to be able to do that. So, but however, you can see that this kind of arrangement is not quite standard as you compare to the conventional and induction motor driver, like inverter. I think last we had this circuitry. So now then you can see that this power module, three-phase power module, will be widely available. You can buy it really common, low cost. This driver, this circuitry is not available, not quite available. So now then, if you're provided with these inverter modules, how are you going to, can you use this circuitry to connect to SR motor? You think about that, how we can do that. So that is to say, if we now provide you this power module, like on, so that's what you're going to provide it. So that's what we're going to have in the market. That's widely available. But now then, our motor drive requirement will be this. So you can use a few of this, or one, or two, or three. How are you going to connect this for SR motor? Think about that.
The speed is variable, right? From channel, speed 1, 2, and 3, right?
So this is only a kind of the arrangement, how we connect the IGBT together. You see, for standard inverter module, that's the thing you can buy from the market. So two transistors will be connected at the midpoint here. Because this point is prepared for you to connect to the induction motor. But however, you can see that in here, you don't connect these 2 points together. You need to split them to prepare for a winding plate here. So that makes it become difficult because we cannot split them. It's already provided by the manufacturer. They already sold it together. So that's the question. What you can do about it. Of course, you can use other configuration, but what you can do.
I was thinking, I used to I worked on my AC, right? My house AC unit, a motor went out. And then I bought a universal motor, but then my control was the same. So what I did was, you know how like that looks very similar, like from one of the line, like up and down. I wouldn't use that as channel 1 or speed 1, and the other one would be speed 2, and then the other one would be speed 3, you know, like you can control it, you know.
You see, for conventional induction motor, what we need to do will be we are energizing a so-called 120-degree phase angle between any one of them. So for instance, this is 0 degree, this will be 120, this will plus 240 in order to have phase difference. So the voltage will be generated from here, as you see from my lecture notes, will be, we have tried to say sideways here, that was sideways minus 120 and sideways minus 240, right? So they continuously have power signal coming out to connect to induction motor. Of course, how we do that will be turn on and turn off by using so-called PWM in here. We create PWM waveform at each of the point here. This point of voltage will look like sideways. Although they're square wave, but they're not exactly a square wave, but more look like sideways. So now then, that is a standard method we use for all the induction motor. Induction motor is quite a large market share, more than 60%. So this is really low cost. But now then, this is available. That driver is not available. How we can, if we ask you to do that, you can use discrete component. You can buy a few IGBT and down to do that, but really impossible, right? Quite inconvenient. So how are you going to do that? Can you use this one to build SR driver? That's one of the questions will appear in the quiz 2 and the final exam. Right? Whoever comes to my lecture, then you can enjoy a benefit from that discussion. So the answer is, do you? Any clue?
I can give in a suggestion. Maybe you could solder the winding in between one of the two transistors, the two IGBTs, and then connect it the other end to the other end of the two.
That is
like right in the middle.
That is my understanding. Right? So what you need to do will be, for instance, you connect phase A in here, and phase B, of course, you need to use more power module to do that. Yeah? You cannot only using one, you need to double. You do need to double that. Yeah. And so we just buy another set of the power modules, and then you need to connect in such a way. So you can see that by using this method, the behavior of this and that will be exactly the same. So what happened here is when you want to energize the phase A winding, then this will be on, this will be on. So the current will just flowing through in this way. Right? So next, if you want to demagnetize it, then you turn off these two transistors, and this current still need to continue to flow, right? What happened here will be this will therefore flow through this diode back to the DC source, right? Automatically through this diode. You don't need to do anything, you through this diode. So behavior is the same, but what happened here will be you're raising 4 components, because you can see that in here, this component is no longer can be used. This component is no longer can be used in the circuitry, just redundancy. But because the availability of this power module does not exist in the world, so you have to do that. Okay. Really, you just waste, you need to double your power module. So that's how the connection look like. All right. Any question? So that's the standard method we use. All the people learning on SR driver, we cannot buy this. It's impossible. Not available in the market. You're either using discrete component to build yourself, or just to buy the standard power module, 3-phase induction motor power module to do that. All right. And then one thing you can see that will be when we energize each of the phases here. So when we want to have a torque coming off from this winding, we energize them, we have current pass through, right? But however, when we approach to the alignment, then we need to turn off the transistor. So you can see that the curve will be like that. So when the inductance, let me see. Oh. I forgot to bring my pen, so put annotation. So now that if the inductance is going up in such a way, then the L will like that. We're expecting the torque, the current, the torque will be like that. And of course, our current waveform, we also like to like that. So at this point, we need to turn off, right? Turn off. So that's a usual thing we need to do that. So when we turn off the current here, we like it to stop instantly. But the thing is for inductor, the current never can stop instantly because there's energy inside here. So usually what you can see is not an ideal case like a square waveform like that. So the current will going to be just reduced slowly with a tail. So that's what actually happened. So what happened here, this current instead of like that, the current will probably will do it like that. So that's related. So that's why you may still experience some torque, negative torque for some short period of time. So that means the current is like that. If we draw the torque with the torque waveform, the torque, you may still see some negative torque here, something like this for a short period of time until this current die to zero. So now then, if your boss asks you, I don't like this electric torque, what can you do? Yes?
End your current impulses sooner, or just turn off the firing circuit sooner so that
Yeah.
has time to dissipate.
That's a really good answer. So one thing you can do, instead of turn off here, you turn off sooner. Here, so the current die down, you just balance. So this may seem like negative torque, but you just move it across sooner. So that's something you need to make some decision. How soon you need to turn off properly. So there's some calculation and more detailed design probably in the future when you join my team, become my business student, I'll show you how to do that. So we have to do sooner. Another method we can do would be, I like to have second thought. More second possibility, second way you can do that. That's a very good method. What's the second way? My lecture here is to ask you how to think about a solution. What else we can do to have eliminate that tail curve? Yes?
So say again, we can be amount of magnetic flux value helps to the circuit.
We can get much faster than usual. How we can do that? We do need to modify something, right? Not just directly the same connection, we need to do something. Instead, using a timing control, right? Turn off it earlier, we can make something to reduce the current much faster, much quicker, reduce the tail current, and we can. Any? Yes. Okay, this is the first step.
Short something to ground, and give something directly to.
Yes, sort of. You need to more precise. Yeah, something like that. You see something?
No, so you see that turn on switch 2, the short ground, or the turn on the ground short switch.
You really get the answer, right? You see this current is going in this direction. So the current will actually go in here, return to the source. So we need to have, so this current will opposite direction to the input voltage.
Yeah.
So that means if we want to reduce the voltage reduce the current much faster, we can increase this voltage. Of course, we cannot increase like that. We need to boost. Yes, that's the good term. Boost the voltage. So what we can do here, we have put additional voltage here. So this more voltage is that here we connect to here. So this dial here, we don't connect here, we connect dial to here. Then we can have a higher, so we have normal voltage to energize the winding, but we have a higher voltage to demagnetize it. So this can therefore we do much quicker. We just return more energy much quicker to DC source. So we call it boost voltage. That's the term we tend to use, right? So that's how we design a machine, how to make the design machine much better. So then we do have a many techniques. We know the SR motor have a lot of advantage, really good, also a lot of drawback. So we do have a lot of technique to eliminate, to reduce all the drawback. So that's how we conduct a research, how to make the motor become more useful, reliable, low cost. All right. Any questions? Yes.
Is it possible to use the inductor's energy to power the next set of
Yes, yes. Now this energy instead return to this main source, return here, and then we need to connect these two up. We haven't finished that yet. So may possibly now we try to build a DC converter between this and that. So we return this energy to here. So next time we can use this energy to power other phases. Because this is a main input energy, that's the power generation, right? Yes.
Does the time constant decrease if the S2 is turned on for inductor A? I forget how the discharge rate is affected by the voltage across the inductor.
So that mainly relate to how the time constant in inductor and storage will here.
Yeah.
So that means when we charge it, S1 and S2 turn on, we fill up the half L1 square, become a current here, and this energy will need to be charged back to the DC source. So normally this calculator will quite large. So we did a lot of calculation how to be maritime property. But one thing you can see that if we do have a high boost voltage here, we can able to discharge really quickly. But how fast, how quickly, we don't like to do. And but the high voltage, you need to have more investment. And so that's why there's a lot of compromise in the SR motor design. Well, a lot of interesting work here. So that's why nowadays we only research on SR motor, nobody work on induction motor or DC motor. We cannot publish any paper, we cannot any more advancement. Because we can see that SR motor do have a really good potential. It's really good for fire application, for fire control system, for some really reliable application. Because this motor is highly reliable. Anyway. Need to how do I need to turn it off first. Where is it? So for normal SRM driver system, like in here, so this is 6-4, so we have 3 phases. So this will be connected to a winding in here, this B phase winding and C phase winding. And then we usually to detect the current because we really have to conduct current control. Exact current control is not covered here, but will be in the future topic. And then we do need to have position sensor. As you know that we need to energize the state winding when the motor go near to the alignment. So that's why there's a lot of the position sensor will be really important here. So that is to say, you can see the control loop here. We will position sensor, the firing signal for all the transistors here, and then we need to detect the current. So we do have current control to program the driver. So we usually to have turn on and turn off the transistor properly. But however, one thing you can see that when the motor rotating at really slow speed, we are able to do that. So for instance, at 300 RPM, it's no problem to do that. But when we go for very high-speed operation, as we mentioned, this motor can go up to 10,000 RPM or 50,000 RPM. Such a high speed, we don't have any transistor, we don't have any chip able to do so high speed. You see, like what we're doing for brushless lattice motor, we need to use PWM, high speed PWM to control the current. So the way to control the current here will be the same. We need to turn on, turn off the transistor to do that. But when we go to really high speed, 50,000 RPM, 100,000 RPM, we can't do that. Then we use other method to control that. Instead using PWM, we use other method to control the current. So we only turn on and turn off the winding once heavy alignment. So in theory, for instance here, if we want the current, let me see. If we like the current to be like that, so actually what happens will be similar to brushless lattice motor. We just turn the current, we will turn the current in this kind of manner. So the transistor we're going to turn on in really high speed, like what we did in the brushless lattice motor. So instead of on and off like that, we'll using PWM to control the current profile. And for really high speed, we do have a method. We only turn on once on and off, we're able to control the current profile. So that's a more complicated control method. But you need to go to postgrad. I will show you how that can be done. So in here, just to tell you, we do have another current control on and off control method for the SRM. So we all using digital method rather than in the industrial motor, we use simple sinusoidal PWM. So again, to connect the phase winding, as you see that we have the pole pair. Each stator we got the pole pair. So that will say, for instance, for A phase, we got this pole pair, then these two will connect in series with the same kind of the winding direction, so that the thrust will produce same kind of the thrust through the rotor. So these two connect in series and then connect to between the two transistors. So that's how we're going to wire up. Have a quick look of this diagram. Do you get the point how we wire up all the winding? So each of phase, for instance, we call it phase A and A dash, they will connect in series. So the current will go the same kind of winding, will ensure the thrust will have the same direction. And then these two connect in series and appear in here. And same as B and C phases. Okay. So in a sense, you need to know how to do the connection. All right. Let me give you a paper. In the final exam, there will be some online, as I seen before, multiple choices. And also there will be hard copy, hard paper. You need to sketch some drawing. For instance, sketch how to do the phase lighting and sketch how to connect the phase A, B to some standard power model. So because for chemists, you cannot do any drawing properly. So I do have a two set of the thing for you to do. Online soft pressure and MC, and also on paper I had to do all drawing and equations.
We should bring our computer.
Yes, please bring both your computer and also your pen.
From now on, are we gonna consider the first inverter model you showed, or are we only gonna consider the common inverter model that can be used in the induction motor, and we're just using it here now?
So the standard circuitry for the SR motor will be this way. But this for some additional information in the future, when you want to use standard three-phase inverter module, how we do the winding connection.
Oh, never mind. Okay, I see.
So this one is also available, but really expensive because very few people use it. This inverter module is widely available, so that's a comment I have. I hope maybe in the future we can manufacture this kind of model so that we are able to sell the SRM much cheaper than before. So now then, one thing you can see that will be we do have so many transistors here. Especially when we go for inverter power module, we need to have more transistors than looks so. So we want to find a way can we reduce the number of the transistors in the total system. So this is also one of the interesting work we have been working on. In this one of the configuration. So this is called the N+1 topology. So have a quick thing about it. So that's for three-phase. Yeah. Can you have a quick look how it works, or you can help me to tell how the operation look like, how we energize the winding, how we demand times the winding.
You only use one MOSFET for all three windings, and then all the other three windings have their like appropriate MOSFETs for going on, for making them. And there's a capacitor. What is the capacitor used for?
Yeah.
The capacitor.
Have you got clue? Quite straightforward, right? No, it's not complicated. So that to say you are able to keep one common transistor to share all the excitation current. So with this one, of course, the current will go through here, the metal part, the A winding. So we turn off, this current can therefore return to here, and then this current will pass through this winding and return to the source. So that's one of the ways we can do.
And then the access voltage would go to the capacitor.
Yeah, that's a good point. Why we took capacitor? Because usually for DC voltage input here, we want to stabilize the voltage. But the voltage usually with battery, then the response for high frequency may not be too good anyway. But if we use high frequency switching, because we need to control the current, in this case, the switching frequency for all the transistors can be 20 kilohertz or maybe even higher. For that high frequency, the battery or DC source may not be good enough. So we do have capacitor here. We call it decoupling capacitor to decouple all the noise issue. So just look like a filter, provide high speed of the current support or voltage support to the switching. If you don't have this one, you're expecting all the high frequency generating here will go through the DC source, will try to assume your DC source will absorb all the high frequency switching. Hopefully that is not sufficient. So that's why for all the, even though for inverter here, you do put the capacitor. Centrally, you put a capacitor for the. So this topology, we call it N+1 because N is the number of phases, plus 1 means this additional transistor. So that's how we call it, okay? So for instance, in the exam, I ask you, can you sketch the N+1 topology for SR motor for 3 phase? Then you need to know how to do that. If for 4 phase, then that means this 1, 2, 3, and 4, right? If in the exam, I give you X6 SR motor, can you use N+1 to sketch it? Then you need to know how to do it, right?
No, you just repeat.
Yeah, you just repeat one more phase. S1, 2, 3, and put that S4 for the 4th phase. And then how to connect them. So you need to have a clear mind how to reconfigure the connection. The things nowadays, when we are motor design, not only purely magnetic winding, you think about how to control the winding, how to use the power electronic control the motor. So nowadays, power electronic and motor and machine cannot separate. We need to put them together. Okay, so now then let's see other possible topology. So before we go, this I just sketch you the how the joint look like. Okay. Where's my pen? Yeah. So that means for this one, when we energize it, then this will turn on like this. That's when we're on. And then when you off, then this current will therefore flow through in here. Like that. Okay. So that's why when we develop the winding, we still need to turn off Q1. Do that. When develop it, this turn on here, develop this need to be off.
Each winding has two ovals.
Using different color to
This
represent
is a three-phase motor, right? This is
three-phase, three winding. Yes?
What is the source of the parallel passive?
Oh, we just said that because this is quite a high frequencies, so we want a capacitor to filter all the high frequency loss. We call it decoupled. Because this may connect to a battery, maybe a simple DC source, it's not high frequency. The frequency we're using here could be 200 kilohertz, maybe 50 kilohertz. So we do need capacitor. The capacitor also used for other motor driver, like industrial motor driver, we also use capacitor. So that's to say, we usually have a capacitor in between there. It's also very common. So that means in the exam, if you sketch this one, you put a capacitor in here, you got some bonus mark because that shows you understand the driver operation. We do need a capacitor really close to the transistor. So this capacitor really much close to this, not in here, but will be really much close to the power module. Yes.
For electric vehicles, which one is used more, switch reluctance motor or a induction motor? Or not, maybe I should say brushless DC motor. Because I imagine this topology is more simpler than a brushless DC inverter.
That's right. Yeah, at the moment today, the still brushless DC are more popular in electric vehicle. Why is that? Because already highly mature. But this one is not mature. Although seem low cost, but still not that mature. Although highly reliable, but still not mature. Popular is your duty how to promote this motor for our next generation of electric vehicle. But not only electric vehicle, aircraft. Aircraft will be more important because aircraft is 100% reliable.
You don't want something.
In a own vehicle, you can just stop the vehicle, you can go. But up in the air or maybe electric vessel, you see, you know that for electric vessel is all the motor battery must be more reliable than vehicle than car. Because you're not expecting everybody can swim in the middle of the ocean. What you can do? We can't do anything. So for reliability issue, aircraft is the first, vessel boat is the second, third you go to the car.
Makes sense.
So that's how the current look like, right? So you can able to draw the interfaces. So this is another possible configuration. So you can see the SR model has so many research topics, so many things we can work on. So now then, can you, for this diagram, can you tell me what happened to this diagram?
It's kind of like a transformer with the
Transformer, yeah, transformer. So we put a transformer inside the motor to demagnetize. We do the demagnetize. So the demagnetization for any winding, we don't need to have the same winding. Just like a transformer, you can demagnetize in the segment design. So that's the power design. We magnetize it, and then we demagnetize it, then we transfer to this winding for demagnetization. So we need a double wire, but double wiring for each one of the phase. Right, so that's all. Yeah.
Has the efficiency of these models been tested yet or not?
The efficiency depends on many design issues. For instance, if you want, before I answer that, I need to ask you, what's the key advantage using two winding for any one of these? Yeah, of course, it relates to efficiency. Sometimes the efficiency will be one point. Another point will be how we able to control the torque. Also, the torque report, like what we mentioned just now. But this kind of circuitry do have a good advantage for the torque report control. Although in here say each phase by two winding, one for excitation, one for return path. It seems you can reduce the component, right? Because in this case, you can reduce one transistor, the one power on each phase. But there's another important point I did not say here, related to performance or probability efficiency. What can you think about that? You think about you just now mentioned good for a transformer. What is the transformer current? Look like something like that, yeah. We think about the current. How the current we can able to have the torque report control or the electric torque the power generation. What? You see when you develop a motor, the number of transistors, although you may think is expensive, but the transistor only just a few dollars, motor a few $100. So that means the cost in the transistor is not important. Because more importantly is the performance. You see, in here, we just reduce one power and one transistor, although you can save at $1 to $2, but it's not that important compared to overall vehicle performance. So in here, we do have embedded advantage, which will be more important than saving one transistor and one power. What is it? Related to the transformer. What transformer behavior can help you to control the motor current or motor torque? Think about that. You see, transformer winding, we can using turn ratio to control the secondary side current. You can draw more current from the secondary side, right? Why we want to draw more current from the secondary side?
Oh, behind test faster.
Demagnetization, yes.
Oh,
Good point. Yeah, good point. I need to give you bonus point. Yeah. So you should follow me to do a PhD. You're so smart, right? Anyway, so if we reduce the number of current here, we can increase the current. We can have large current here, and really quickly can demagnetize the current to reduce the negative torque report. So that's also a good advantage. By using this bi-five winding, we are able to have the SR motor. Okay. So there's another interesting circuitry called the C-dump topology. So each winding are connected by S, right? By the switch. When you turn on, obviously we can do that. When you turn on S, then we can verify each of the phase. So when S turn on, the energy stored in the phase will return to the capacitor CB, right? Yeah, that's pretty good. The energy stored in the CB are delivered to the source input voltage Vs by combining some component. So tell me, anybody can supplement about how the advantage on operation, why we need to do that, what kind of saving we have. Obviously, you can see that by using this step, but each of phase, we reduce one transistor, reduce one diode, right? And then, so the excitation will be the same, but the demagnetization will be different. how different it is. So when we turn off the transistor here, this energy will therefore go charge in here. No, it's just very charged up in here. So you got energy stored in CD capacitor. But we do not allow this capacitor to overcharge. Because every cycle, all the energy from here, charge in here, we do a profit. This voltage going up. So we need to de-energize the capacitor. Then by using this transistor. That's why this converter, we conduct this energy, we turn it to the source. So this will look like another secondary side DC to DC converter will deliver energy from here back to the DC source. And then because this is a DC converter, you can actually using DC-based control to control how fast, how quickly, how much energy return to the DC source. So that's why this will have a combination facility. They're able to convert voltage. So you can see that we do in the research topic, we do another method. We can assist the SR motor to control the torque, control the current, excite the winding, and demagnetize the winding. So that's why just in the circuit research, we do have a lot of work that can be done. So let's discuss the typical waveform we are having for each one of the phase. How we combine all the torque, ripple, or all the torque for each phase together. So in here you can see that, for example, in the phase A, when the inductance will increase with the phase angle. So with the rotor angle, and then you therefore after alignment here, this point, you will decrease it. So in that time, we usually will be inject with a current in the winding. So that's why this will produce the torque. So after this phase A go to the torque, we do need to go to another phase. Another phase should have an increasing for the inductance profile. So within that time, we should have a current go to the next phase and so on. So you can see that in here, we need to control the timing really carefully, really precise. If you don't do it properly, and probably there's a gap here, or maybe overlapping here, then the top profile may not be looking too good. So that is something quite important for the machine design and the control design, and the geometry design too. So that's why people always complain about this SR motor. You have torque ripple issue because you do need to control this all the overlapping, this gap really good. Make sure they will overlap or they will join each other without any gap or without overlapping. So that's how we're trying to design the motor. So that's roughly what we need to do for the four-phase machine. We need to do it one by one. So each time we have one torque coming out, when we have current, we got one torque. So you can imagine the torque also look like this profile. So four of them together will therefore can able to control the overall torque become a linear all over the rotor angle. All right, that's how we come out. So here will be a really quick tutorial, very simple tutorial. Show us how to calculate the torque. For instance, we got X6 SR motor. So that is to say X stator pole and 6 rotor pole have an inductance profile, which will be equal to this one. So then I have typo in the next note. I'm going to change it. Then that will be in the page 48 previous page. So that means the profile will be like that. So that means it's 70 millihenry per 15 degree. And then now if the current for each phase, so this current is 16 amp. So calculate the motor torque. So we do have formula like this. What we need to do, I need to turn off this. So what we need to do here will be get the LD theta. So that's a 15 degree. We need to change it into radian per second. So that will become our Henry per radian, and then substitute into this equation. That's it. That will be 34.2 Newton meter. So that is to say that for the top pole, then we can. Where's the pen? Then if you can see the top ripple, the top, then we can see that one of the top will be like that for A, and then that's A. And top B, then we can see that will be like that. And so on for top C, and probably then will be like that. And then all the top add together, you can see that the total top will just adding all the thing together. Then of course you can see that will become linear top. Putting all together. They don't have all overlapping. We try not to have all overlapping among them. Then we have a linear constant top like this. So that means the motor torque will just simply using this simple formula, you can therefore calculate the motor torque. So you can see that the design of this motor are quite straightforward, quite simple. But the key thing will be how to design the geometry, make sure that all the stator pole and motor pole geometry will be designed properly so that we don't have a problem of all this load overlapping and the gap. So that's a major criteria how we work on this motor. So you can see that this SR motor, the torque is a series of the pulses. So each of these produce a certain amount of the torque pulses. So the torque only can produce when the inductance are changed. When we have a DL d theta, which is greater than 0, then we're able to produce a positive torque. But if the inductance decreasing, then the torque becomes negative. So that means when we approach the alignment, we can see the positive torque. Away from the alignment will be negative torque. So you see the torque will be a summation of all the discrete torque log overlapping, put them all together. So one thing will be like that. You can see that the torque, so the torque will be actually putting all these things together, right? So if one of the phase is broken by any mistake, then probably you will see the torque will be like that. One of the phase will be disappear here. So that means you can see the overall or the average will be lower by certain amount here by the missing phases, but we're still able to continue to control the motor. So that is to say why we call this motor with fault tolerance, because each of the phase, like in here, for example, like A, B, C, if D is broken, then we still have phase A, B, C produce the motor torque. We just have higher torque ripple. So when the motor go to phase D, it's just missing the torque there. So the motor is still able to continue to run. You won't have too much disaster. But for industrial motor, DC motor, any one phase broken, the motor will not working at all. So that's why this motor do have so-called the fault tolerance. In case any one phase malfunctioning, then the overall torque can still produce, but we do have a kind of ripple torque appear. Then for this motor, when we try to compare with industrial motor or other PMSM, I haven't teach you about PMSM yet. PMSM is a permanent synchronous motor. It's similar to industrial motor. Industrial motor, we got the rotor bar in the center, but for PMSM, we using the permanent magnet to replace the motor bar. So it's another type of the motor, but we not that have a good market share, so I did not cover in that syllabus. But anyway, for this kind of industrial motor, when we compare to the SR motor, we find that all these conventional motor, all their torque are more smooth. because the torque are actually produced by the sinusoidal equation. So you can see that we are able to produce a constant torque for all this conventional induction motor or PMSM. But for this SR motor, then we use multiple phases. Each phase will produce the discrete torque, which may not be so welcome in some application. So that means a lot of research we need to conduct, try to smooth out all the torque, make sure the torque will be smoother, how to control the torque profile properly. So on this conventional motor, we are able to produce the torque simultaneously and constantly all the time. So let's finally try to review all the SR motor key feature. So SR motor can see that they're highly nonlinear. Even the torque equation are proportional to I squared. First is nonlinear according to the current control and also proportional to the induction profile. So that means this kind of the highly nonlinear will be one of the issue of this motor. But SR motor do have a really good starting torque. In the next few slides, we're going to discuss why the motor have a very high starting torque. I think we do discuss briefly about that, mainly relate to the back EMF. So SR motor, if you do have a high starting torque, then it's really good for working in some high power application like the electric vehicle. We can have high starting torque. We can able to speed up the motor really quickly. And the motor can able to perform the power regeneration. You can see that when the DL deflator is increasing, we are motoring, and vice versa become generating. So this motor, we can very easily program them become a generator. So you can see that most of generation, we do have a permanent for the power generation. But for this kind of the motor, we can just control the turn on and turn off angle. Then we're able to use the regeneration mode to generate the current. So that's one of the key things is this motor, we also use them really often in the power generation. And the rotation direction is not controlled by current. As you see that it's only controlled by the sequence of the stator excitation. Just like you can see that when we excite A, B, C, D, then the rotor will anti-clockwise, and we excite in another direction, we can change the rotor rotational direction. So this motor, of course, we can use for quadrant control because we see that a motor itself, we can able to have power generation and motoring. Then quadrant control, that means we are able to forward motoring, forward control power regeneration, so we can all do that. So this motor really good for quadrant control too. So the motor is nonlinear. So that means if you want to generate an equivalent circuit model, it's quite difficult. You see for induction motor, we can able to generate T model without any problem. Even though for DC motor, we also have a circuit model. But here, I did not show you any circuit model for the motor because they're not linear. I don't have any particular circuit to show you how it works. So that's why this circuit, we call it highly nonlinear, mainly because the feature itself is difficult for us to analyze them properly. So to analyze them, to understand operation, we do have technique called the finite element analysis. So the finite element analysis called the FEA is quite a well-developed software. We're able to look into the magnetic flux inside, the torque inside. So what we need to do using finite element, we can just draw the motor, energize them with the winding, then you come up with all the magnetic field, how it look like. And then we can use them to calculate the magnetic torque. So that's how we analyze the motor. We don't have any simple circuit model or equivalent circuit model to examine the motor, I'm afraid. So conventional AC motor, including induction motor or just like the synchronous motor, they all based on the rotating magnetic field. The rotating magnetic field are sinusoidal. So like the induction motor, you can see that rotating magnetic flux are sinusoidal. But SR motor, everything will be pulsational. All the pulses are discrete stator current. So that means also of the inductance, although in my lecture notes are all constant inductance, but actually the inductance is not constant. You see the inductance change with the position, even though the inductance will change with the current because the saturation of magnetic property. For my analysis here, I sometimes assume the inductance does not change with the current, but actually it do change with the current. So that's why it become more complicated when we want to analyze the motor. So probably after this few lecture, you now understand why this SR motor is not that popular. Because the feature, the characteristic, like the current profile, torque profile, each of phase excitation do require a lot of the technique. If different from DC motor or induction motor, which is energized by simple three phase, then work. Although the concept is quite complicated, when we convert induction motor into a T model, we need a lot of the mathematics. But overall operation control are quite simple. But for SR motor, you can see that a lot of the nonlinear, like the inductance profile are nonlinear. The turn on turn angle are quite complicated. We need to deal with the regen torque issue. So that's why this motor, the operation control are need to really precise. Another thing I like to discuss will be the torque, high starting torque. You see this motor, the torque is especially quite high. So why is that? You can see that the torque equation have LIDL theta. So that to say, the proportional I square. Other motor usually only proportional to current I, like this motor, only proportional current. But it's proportional I square. So that to say, if you inject any current, the torque you can boost up with the current in square wave manner. So that's why you're able to firstly using current to control with a high starting torque. Even though the motor is stationary, stand still, you inject a current, then you're able to produce the torque really significantly. Another would be the back EMF. Do you know, remember our equation 14.5, we do have the first term have this term, which is the back EMF. I think go back to the equation, let's quickly go through the. So we do have a term here, right? So that means at the standstill, then we are able, this speed will become zero. So all the input voltage will only rely on these two. So probably in this case, during the standstill, all this back EMF will disappear, equal to zero. So that means in the starting, we don't need very high voltage. We can still able to generate high variation of the current. So that's the thing we quite like. So for this motor, we inherently deliberately able to have a really high torque capability because the back EMF equal to zero at the starting. Another thing would be so-called a direct magnetic pull. The torque is actually produced by simple magnetic attraction between the reluctant force. So when the rotor approach to the alignment, so the reluctant force actually really high. So to pull the rotor to the first alignment. So this method is inherently produced in the SR motor. It's not using the Lenz law to do that. So that's using another principle able to produce the magnetic pull. So that's also make the starting torque become really high. Then this motor, as I mentioned, also really good for power generator. So one thing you can see that in here, this is the motoring. This actually is power generation. So when we want to operate this motor as a generator, of course we need to have electric torque. Electric torque in here means we are inputting the energy to the motor, become a generator. So we can control the turn on and turn off angle to make sure that you have more portion of the operation in this region. Then you automatically can become a generator. So we only excite the winding firstly from the DC source, and then we allow the current to energize, to demagnetize here. Demagnetize means we return energy to the DC source. So that means this motor is quite friendly. So that means we do this as a little bit of energy to charge up the inductor here first. And then the external force, like the generator force, like the hydropower, whatever, will move the motor as a power generation, and that the energy will therefore develop in this portion of the section. So this will be current and return back into the DC source to become a generator. So the operation will be the same. From this curve, you can see that how this motor can very easily to work on the turn on and turn off angle in order to produce the power generation. So now the question will be how you turn on the transistor will become generator. So that's the basic characteristic, right? Usually when this motor for motoring turn on here, turn off here, right? But now then, what you can do to make it become a generator, how to turn on, how to turn off. To change the motor become generator. No, turn on later, turn on later. You think the turn on angle and off angle are the same as before for power generation.
It's probably just in, you, shift the phase of the control signal. Is that.
Where it's at the top right now. So let's just like going backward.
You see, in that mode, the current here are returned through the diode. Whenever we got sufficient energy in here, the current still return through the diode. So we don't have to do anything. Then automatically we can return more. Then the motor is in power regeneration. So that means we got negative torque here. When we have less motoring torque here, because when this generation, this torque will be much smaller. We don't need any. So that means this amount of energy requirement will be much less. So automatically the motor will store less energy in the motoring. You automatically can generate more current due to input from the electric torque here to produce the current in that. So it all can be done automatically as long as we can do an external force to drive the shaft. We can able to return more energy during the generation. So actually the operation are very similar to induction motor. Induction motor, how to make it into power generation, the actually PWM will be pretty much the same. What we need to do is to reduce the changing the frequency, the sleep frequency into negative. Well, just this will be using the frequency, but this might be not using other things. Yes.
So does that mean when you're driving it forward, it's always also regenerating as we're trying to drive it forward?
Yeah. That's why when we do the motoring, we need to control it always become motoring. So that means we have to really quickly to turn off here or turn off earlier to eliminate this negative torque. But for power regeneration, we don't need to turn on earlier, we just turn here, we turn on later. So the alarm more electrical. So that means we alarm the power generation. So that's why first you can see that the current is unipolar, always single direction. We use single direction of current, you can still able to produce the power generation and the motoring. Motoring and also power generation have the same direction of current. So it's different from the DC motor. DC motor, when we have power generation, the current will be reversed. Similar to induction motor, then the current look like reversed. For this one is a unipolar current, also during the power generation mode. And the control of motor rotation also quite straightforward. We have been discussing that. So mainly relate to the phase sequence. So in these two diagrams, so this is the diagram we have seen in the past. If our phase sequence is from this one A and energize B, energize C, energize D, you can see that the rotor rotate in this direction. Because when energize A, we got this alignment here, and then next, and then when energize C, so this will rotate to match up between these two, then you can see that the rotation will be anti-clockwise. So that means when we have a clockwise sequence A, B, C, D, then the rotation of rotor will be anti-clockwise. And then now then, if we do it in another way, like in here, A, if we energize D first, then we have this alignment here. And then when we energize C, we got another alignment here. So you can see that we only change from A, B, C, D to A, D, C, B, change the sequence. We can therefore change the rotation. Very straightforward. That's what we have been doing. So for the motor rotation, we don't change the current. We only change the phase sequence. For induction motor, I'm not quite sure you know how to change the motor rotational direction. I think you need to know that. So for instance, for induction motor, that's inverter. So we connect, so we have three phases A, B, C. For example, A, B, C, then we connect to our motor. So that means A will be equal to something like sine omega t, right? B will be something like sine omega t minus 120. And C phase will be sine omega t minus 240, right? So how do you change the induction motor rotational direction? So with this one, using this one, the motor rotate forward. How do you reverse the rotation? Yes?
You switch the clockwise A and C rules connected.
So that means what's the equation for A, B, C? You need to control it to reverse rotation.
Yeah. Wait, which one?
Now, if using A, B, C, this sine wave waveform, because the induction motor makes a sine wave waveform. So A, B, C, the sine wave waveform will be typically omega t, then phase difference 130 and 240, right?
Yeah.
So this A, B, C waveform will put on the induction motor, then you rotate, say, in the forward rotation. Now then, if I ask you to change the rotational direction, reverse the direction, how are you going to control the pulses for A, B, and C? Yes?
I imagine you just flip the sign, the plus 120 and plus 240.
Yes, correct. Yeah. So what you need to do to change that into just change the direction. There's another method to do that. instead of changing these ABC pulses, in the wiring connection, another method to reverse the rotation will be, yes,
You swap the positions of connection to B and C.
you just swap these two. Then you also similar to what we did here. So that means you don't need to reprogram your computer, right? You just swap two wire. So in the future, if you go to any website, the industrial motor rotating instrument, you just swap the two phase like this, then you can change the another rotation.
Where can you swap any two wires?
Only swap two.
Okay.
Then you automatically change the phase sequence. When you swap BC, you just change from ABC, then become ACB, then you just change the phase sequence. So basically, we change the phase sequence in order to change the rotational direction. You can try that at home. If you do have any inverter and motor and inverter driver, you swap the two wires, then change the rotational direction. So that's a practical skill, how we're going to control the motor, right? Anyway. So that means in here, the torque and speed are actually, we are using this kind of the converter circuitry to control it. And then we do need to have a controllable converter to control all the things we mentioned just now, including turn on angle and turn off angle. So this kind of SR motor obviously will be variable speed because we just change the phase sequence speed. You can also change the speed of the motor. We need a rotor position sensor because the phase sequence speed is correlated to the rotational speed. So we need to make sure that we can able to catch up with the rotor. But again, in here, each phase will be independent. So that's why when you construct this kind of the converter system, then you need to understand how we fire each of the phase properly. So you see all the converter are more look like we have a switch in series with each of the phase connect to the DC source. So in case any one of the phase is broken, you can use the switch to isolate from the DC source. As I mentioned just now, if S1, S2, you can connect in series with the winding. Any one phase have short circuit. You see some of the winding do have short circuit due to the flashover. Some of winding, the enamel wire, the coating is broken. Then we have some winding short circuit. It happens quite often. So that's why if you see some winding have a problem, then for this kind of SR motor, you can automatically demagnetize or disconnect the winding and protect the motor. And the motor can still continue to operate. But for industrial motor, it's different. Then if any one of the phase have short circuit, then you can't do anything. The motor needs to be completely stop operation. So that's why to use industrial motor or synchronous motor or DC bus motor for electric vehicle, any winding is broken, nothing you can do. But for SR motor, you still can continue to run the motor until you go for the next service. Of course, the motor do have a lot of hot recall during that time, but it's much better than the motor need to completely stop. So time's up, right? So we'll continue that for next Monday. We're going to finish question and then we do revision. And then on Wednesday, we'll go to the phase 2. And also tomorrow, we got extra credit for the industrial motor log motor test and block motor test, right? I see that tomorrow many people sign up. I don't think the lab can accommodate that many. So
There's also some next week.
yeah, if you find it too cloudy, you can go to the following week.
Yeah, we're next week.
Yeah. So you all can make your own home. If you all come, then probably we only have 2 sets of the kit. So
We're next week.
that's fine. And I see 70% of people sign up for tomorrow. Only 30% sign up for this week. So try to, if you find it too many people there, you can come next week. Okay. So see you probably tomorrow then.